Let's take a look at the next question here. It says, if the wavelength of a light beam were doubled, its frequency would be blank. All right, so remember, guys, light always is a constant speed, which is c, and speed is determined by the wavelength times its frequency, right? So if c is constant, if wavelength is doubled, its frequency to make sure that c is constant has to be halved, okay? So if wavelength is doubled, then frequency has to be halved in order to make sure that c stays the same. Meaning the frequency we need to be halved. B is the correct answer here. All right, so the next question here says, if the energy of a photon is doubled, which of the following properties of the photon will also double? Guys, remember, energy is equal to hf, where h is the Planck's constant, okay? So this means h will not change. It's a constant for a reason. So if you double the energy, only other variable that can double here is the frequency. All right, so frequency is going to double, which is c. The next question here says, if the red line in the Balmer series has a wavelength of 656 nanometers, which of the following is closest to its frequency? All right, so guys, remember, c equals frequency times lambda, where lambda is a wavelength, and c is always a constant. So if we know this value and we know the wavelength, we can easily find out what the frequency is. So let's do that. So what is c? C, as they tell us in the passage, is 3 times 10 to the 8th meters per second. That's equal to the frequency, which we're trying to find, times lambda, which is 656 nanometers, which is the same as 656 times 10 to the negative 9 meters, right? I always like to convert all the units into standard units so as to make sure not to make the mistake of using the wrong units during my calculations and wondering where I went wrong. So let's solve for frequency here. That's going to be 3 times 10 to the 8th meters per second divided by 656 times 10 to the negative 9 meters equals frequency. That's going to be the same as 3 over 56 times 10 to the 17th is equal to the frequency, 656 seconds. And this is essentially very similar to 1 over 200, let's say 200 and let's say around 220. We'll roughly estimate this to be around 660. So this is 1 times 10 to the 17th seconds equals frequency. And so, that's the next question that I have saved down there. But let's move on with this, do the rest of the calculations here. That's essentially 1 over 2.2 times 10 to the second times 10 to the 17th seconds equals the frequency. And so 1 over 2.2, that's going to be around 0.5. And then 10 to the 17th divided by 10 to the second, that's going to be times 10 to the 15th per second. That's the frequency, and that's going to be around 5 times 10 to the 14th per second. That's our frequency here. Now, you'll notice all of our units are in hertz. Well, hertz is the same as 1 over s. So this 5 times 10 to the 14th, that's exactly the same as 5 times 10 to the 14th. 5 times 10 to the 14th per second is the same as 5 times 10 to the 14th hertz. Now, you'll notice there is no 5 here, but the closest answer here is A, 4.6, which does get rounded up to 5. So it is likely that A is going to be our answer here, as it is closest to our calculated value here. The next question here states, which of the following is closest to the wavelength of a photon whose energy is 2 eV? All right, so let's go back to the passage, see if they give us any useful equations here. And we'll notice right here, this is the equation that we're probably going to have to use. Lambda is equal to hc divided by E. Well, h is a Planck's constant. They give us that value here. So h is 4.1 times 10 to the negative 15 eV seconds. We know the speed of light, c. That's 3 times 10 to the 8th meters per second. And we divide that by the energy, which is 2 eV, which is given to us by the problem. So first, I like to make sure that we're not or cancel out any of the units we're not using. We're not using seconds here since these cancel each other out. EVs cancel each other out, and so we're just left with meters. So let's do this too. This is gonna make this is essentially 4 times 10 to the negative 15. So we can cancel that out to 2, and so we end up with 2 times 3, 6 times 10 to the negative 15 times 10 to the 8th. That's going to be 10 to the negative 7 meters. We'll notice that we're looking at nanometers here, so we just multiply this out by the conversion factor, which is going to be 10 to the negative 9 nanometers, or sorry, 10 to the 9th nanometers per meter, right? Cancel these out, and we get 6 times 10 to the 2nd nanometers, or 600 nanometers. So we'll look for the answer that's closest to that, and voila, that's going to be B, 620 nanometers. That's going to be the wavelength of this photon.